Hello everyone. Okay, so today we're going to look at power series, and we'll explain what that is in just a moment, but I want to start with an example here. What is the series that converges to f of x equals 6 over 1 minus x? So I've given you the answer to what it converges to. Now we want to go backwards and find the series. Now if you look at this 6 over 1 minus x, it kind of brings to mind the form of the sum of a geometric series, doesn't it, right? It's a constant over 1 minus something, so that brings that to mind. And if we look then, our first term would be 6, our common ratio would be x, and in order for this to work, x would have to be less than 1, and that's important, right? So if that's the case, then this function would be our first term is 6 plus 6 times x plus, now we're going to multiply by an x again, plus dot, 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 and every time we're multiplying by x, so that would be 6x to the n, and so on, as long as, and here's the catch, the absolute value of x has to be less than 1, so x is trapped between -1 and 1. We found a series that converges to f of x. Yay! Now, that brings us to our definition of a power series. A power series for f of x centered at x equals 0 can be expressed in the form, the summation, as n goes from 0 to infinity, of c sub n x raised to the n. Now this c sub n, that's just a constant. Any constants, okay? And that would be c0, x to the 0, plus c1, x to the 1, plus c sub 2, x squared, plus whatever our constant is, times x to the n. And there we go. Notice it's powers of x's. That's why it's a power series. Now, we don't always have our power series centered at 0. Sometimes it may be centered at a different x value, okay? And a is just some constant. It might be centered at 2, it might be centered at 10, it might be centered at -1. Well, if that's the case, then our power series is the summation as n goes from 0 to infinity of our constant, and now it's x minus our center raised to the n, okay? So remember, this is a constant, and this a is the center. So we would have c sub 0, x minus a to the 0, plus c sub 1, x minus a to the first, plus c sub 2, x minus a squared, and we continue in that pattern, c sub n, x minus a to the n, and it continues infinitely, okay? Now, a power series is also known as a polynomial with an infinite number of terms. An infinite number of terms in a polynomial, well, that's different, okay? Now, we just mentioned a power series, and I want to go back to this first example. So if we look at this example, this series is a power series. And not only that, but both the series and the function are centered at x equals 0. Now we can see that because it's x and x squared, not x minus something. But also, if you look at this interval where x is allowed to be, what's the center between -1 and 1? 0. That's where the center is. And that's why it's centered at 0. Okay? Okay, next we're going to look at finding a power series by using another power series that we know and using derivatives. Now, if you remember back to our day one lesson, we had our very cool example. Remember our very cool example? 1 over 1 minus x, this one. That's 1 plus x squared plus x cubed plus dot, 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 plus x to the n plus, and it continues infinitely, or the summation is n goes from 0 to infinity of x to the n. We now know that this is a power series centered at x equals 0, okay? So, we're keeping that in reserves and we know this fact. We now want to find a power series that represents f of x equals 1 over the quantity 1 minus x squared. So, the one that we know looks like this versus the one that we want looks like this. Remember, this first one is really the quantity 1 minus x raised to the negative 1, whereas the second one is the quantity 1 minus x raised to the negative 2. Now I want you to think for a minute. What's the relationship between these two expressions? If you were to take the derivative of the 1 minus x all raised to the negative 1, we bring down the exponent, keep the inside, decrease the exponent by 1. The derivative of the inside is negative 1, and lo and behold, we get 1 over 1 minus x quantity squared. So we now know that the derivative with respect to x of our very cool example is the function that we want now to express as a power series. So, what can we do? Since this is the derivative, let's differentiate both sides of our very cool example. So in other words, we're going to take the derivative with respect to x of this 1 over 1 minus x equals, and we're going to take the derivative with respect to x of 1 plus x squared plus x cubed plus x to the n and into infinity. Okay. So if we take the derivative on the left-hand side, we already did that work, and we know it's 1 over the quantity 1 minus x squared. Now, if we do the derivative on the other side, the derivative of 1 is 0. I don't really need that, do I? Not really. I don't need to write 0 plus. The derivative of x is 1, plus the derivative of x squared is 2x, plus the derivative of x cubed is 3x squared. And we continue in this pattern. The derivative of x to the n is n, x to the n minus 1. And this continues. Well, guess what? We've found our power series. Oh, let's not forget our limit. That's not going to change our conditions on the end. Remember, up here, which I didn't write originally, we knew that this only worked because this was a geometric. Remember, our a sub 1 was 1, our r was x, and that meant that the absolute value of x had to be less than 1. So negative 1 less than x less than 1. We need that same condition here because we started with that very cool power series. So we have the same condition here. All right, yay. All right, here's another one that I want to express as a power series, very much like the first problem we did today. It's in that formula that reminds me of the geometric sum, right? And if that's the case, our first term would be 1, and our common ratio, it's not x, it's negative x, because, right, this would have to be 1 over 1 minus negative x, okay? Now, remember, that's only going to work if the absolute value of negative x is less than 1. Okay? So let's see what happens. That means we have our function 1 over 1 plus x. Our first term is 1, and we're going to multiply by negative x, so it's minus x. Multiply by negative x, we have plus x squared. Multiply by negative x, it's minus x cubed, plus dot, dot, dot. Now, because the signs are alternating, we need to raise the negative 1. Now, should we raise it to the n or the n plus 1? When n was 0, we got positive. When n was 1, we got negative. When n was 2, we got positive. And when n was 3, we got negative. So we want our exponent, all the odds will give us a negative, and all the evens will give us a positive. So that means we just want to write negative 1 to the n. And then we also need our x to the n, okay? And this continues on. And if we want to write this as a summation, the summation as n goes from 0 to infinity of our general term, negative 1 to the n, x to the n, on, and we need to pay attention to this. Now, if the absolute value of negative x, that's x, right, has to be less than 1, that means negative 1 is less than x is less than 1. That's what we call our interval of convergence. And it also shows again that our center is 0. Now, just like we found a power series by differentiation, we can also find a power series through integration. Now, if we take a look at our function here, f of x is the natural log of 1 plus x. What is f prime of x? Well, derivative of natural log is 1 over whatever you're taking the natural log of times the derivative of the inside, which is just 1. So not only can we look at the derivative, but it also means that the integral of 1 over 1 plus x dx is going to give us the natural log of 1 plus x. Now, this function here should look familiar. That's what we just did in the previous example. Yes? That's the one that we turned into a power series. So we know that as a power series. So what we're going to do is we're going to integrate both sides of the power series we found in the last example. So in other words, we're going to integrate 1 over 1 plus x dx, and that's going to equal the integral of, now what did we have as our answer? We had 1 minus x plus x squared minus x cubed plus dot, 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 plus negative 1 to the n times x to the n plus dot, 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 close it, dx. So now the integral of this piece here, that's our natural log of 1 plus x. And if we integrate on the other side, the antiderivative of 1 is x, minus the antiderivative of x is x squared over 2, plus the antiderivative of x squared, we add 1 to the exponent, divide by the new exponent, minus antiderivative of x cubed, add 1, so we get 4, divide by that new exponent, dot, 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 plus. Now, negative 1 to the n is a constant, so it stays. The antiderivative of x to the n, we add 1 to the exponent, divide by that new exponent, and this continues on infinitely. Now, remember, we had an interval. The x's had to be between negative 1 and 1. It's the only way it works, okay? So this is the answer to our question. That is our power series. But I actually want to go a step further if we could. I want to consider, let's let x be negative 0.5, okay? If we let negative 0.5, that means that the natural log of 1 plus negative 0.5, which, by the way, that's the natural log of 0.5, right? According to our power series, that's going to be negative 0.5 minus negative 0.5 squared over 2 plus negative 0.5 cubed over 3 minus negative 0.5 to the 4th over 4. Let's just do 4 terms. We're only going to do 4 terms. I know it can go on forever, but we're only going to do 4 terms. And then we can go to our calculator and try to put this in. Okay, so let's go see if we can grab a calculator. Okay, so we're going to put in a negative 0.5 minus, then I need a fraction. Don't forget to put your parentheses around a negative number that you want to raise to a power. Out to the bottom, and we divide by 2, get out of my fraction. This time I'm plus. I need another fraction, parentheses, negative 0.5, close it. We're going to raise to the 3rd, get out of my exponent, down to my denominator, divide by 3, out of my fraction. Now I'm going to subtract, fraction template, open, negative 0.5, close it, raise to the 4th, get out of my exponent into the denominator so I can divide by 4 and hit enter. So we have negative about 682. Now let's take a look. What is the actual natural log? And we said when we did 1 plus negative 0.5, that was the natural log of 0.5. And that's the actual value, which is 0.693. That's not too far off. So we said this is about negative 0.682, and the actual value negative 0.693. Now, how can we make a better approximation? So this is an approximation for this. How can we get a better approximation? That's right, we only used 4 terms. If we use more terms, we will have a better approximation. So the infinite number of terms gives us the exact value, but we can't compute an infinite number of values. All right, we're going to stop here for today, and we've done a bit with power series that we will continue in class. I hope you all have a great day. Bye.